What do you see, Sigma?
Just a second. I see two kids are playing hockey on ice.
What did you use for this?
A specialized neural network for automated image captioning.
The idea of combining computer vision and natural language processing gave birth to a neural network which takes an image as input and output a sentence describing what is in the image. This concept is called automatic image captioning. So here is the way it works. First, the input, which is an image, has to pass through a computer vision model in order to get extracted the features from it. Then push those features into NLP model which will output a sentence representing what is in the input image. So in this tutorial, we'll train an NLP model to generate captions and use a pre-trained image classifier to get the features. We'll use attention mechanism in NLP model. So if you don't know about how attention works in a neural network, please watch it before proceeding further. The link is in the description as well as in I button. Let's see how it works in code. First, get the dataset from Kaggle and extract it into your working directory. So in the dataset, you have two directories. One contains captions for corresponding image and it has 5 different captions for an image. And another directory contains actual images. Now we have images as well as their corresponding captions, and here are my hardware and software specifications for this tutorial. So fire up the Jupyter notebook and let's get started. Import the libraries first and set TensorFlow memory growth to enabled so that it won't consume your whole GPU memory at the time of initialization. Now set the path to the directory which contains captions and images. Now take path of file contain token and load it into memory. So for each image there are 5 captions. The number of caption is separated by a hashtag and the caption is separated by tab. So to make it easy, we can store it in a directory where the image name or path act as a key and the value will be a list which contains captions for that particular image. So let's do this. Define a dictionary and start to read each line from annotation file. For each line, get the image name by separating line from hashtag and then get the caption separated by tab. Put the start and end token for caption, then put the caption in the directory where the key is associated image path. You can check it by taking an image path and you can see all its captions are in the list. Let's prepare this data for training. Get the image path and store it in a list, then shuffle it. Now make a list to store captions and list to store corresponding image paths. For every image, get the caption from directory and put them into trained caption list. Then put the image list into image name vector list. Now you can visualize the caption and image. Now make a function to load and pre-process images. Read the image, decode it as JPEG, resize it and pre-process it for Inception v3 model, then return both image and its path. We are using a pre-trained Inception v3 image classifier for feature extraction. Now, a convolutional neural network classifier has two parts. The first which do feature extraction and the second one which act as a classifier. So we need this part only in order to get features from an image. So get the Inception v3 classifier, which is a state-of-the-art model trained on ImageNet dataset. Notice include top equals false represent that the classifier part is not included in the model. Then get the input and output layer of the model and create an instance of feature extraction model. Now create dataset pipeline using TensorFlow dataset and you can increase or decrease batch size according to your GPU memory. Instead of pre-processing images every time at the time of training, we can pre-process now and cache them to avoid unnecessary computation every time. So for each batch of images, get the features by feeding it into feature extraction model, then reshape outcome to 2 dimension. Then for every image in batch, save it in the same directory with the same name where the actual images exist. You can use another directory to cache image, but right now we are going this way. While it's doing pre-processing, let's write a basic function to calculate maximum length of a tensor. This function will be used to calculate largest sequence of words. Now it's time for captions pre-processing. Choose top 5000 vocabularies over all caption and use Keras tokenizer to tokenize caption to words. Then map padding token to 0. Now generate training sequences from captions and convert them into vector by using Keras pad sequence function. This will make each and every caption vector to same length by adding pad token in the end. And here you can use the above function to get the maximum length of caption among all captions. Now we have both images and captions are pre-processed and ready. So let's move to dataset pipeline part. First, we need to divide the dataset into training and validation set. So make a dictionary and put images and their captions in it as we did before. Then shuffle them and split up 80% of the dataset for training and the rest 20% for validation set. Then make lists for training images and captions and iterate through each image path from training keys. Fetch the captions from dictionary and put them into training captions list. Do the same for validation set as well. And you can see the number of training and validation set samples. And with this, the dataset part is done and ready for training. Define training parameter as following, where you can tune batch size or buffer size according to your hardware specifications. Define a mapping function to load the cache features into memory. Now use TensorFlow dataset to make dataset pipeline and map the tensors by using above mapping function. Now shuffle and load the dataset in batches. And now it's time to make model, but let's understand the architecture first. We have an encoder that takes an input and output it features. Then those features will go through a decoder which will output a sentence. Pretty simple, right? Well, it is, but in order to make our model generate more accurate results, we'll use something called self-attention. I've already made a video on it about what it is, its working and what's its need. You can watch it from the link in the description. In this video, we'll look at Bahdanau Attention mechanism. So we know that encoder outputs hidden states, then pass those output and current hidden state of decoder to alignment layer, which will compute alignment score. This tells decoder on which part of encoder's output it needs to pay attention. Then apply softmax layer to convert alignment score to attention weights. These attention weights and hidden states of encoder will be added together to output something called context vector. And output from decoder at last timestamp and context vector will be used by decoder to output next word. And this is how Bahdanau attention works in encoder-decoder architecture. So let's code it. Define a class of Keras model type and according to equation create 3 dense layer to compute alignment score. Then this call function will take output from encoder and current state from decoder in this variable, expand dimensions to represent timestamps from hidden state of decoder. Calculate this part of equation by taking weighted sum of feature and hidden with 10h activation function. Then pass that output to this layer in order to compute the equation and get the alignment score. And if you pass it through a softmax layer, you will have attention weight. Now we have everything to calculate context vector. Just take attention weight and output from encoder and multiply them. Then use TensorFlow reduce sum function to get the sum of elements of above matrix. Now return context vector and attention weight that will be used by decoder. Now make encoder to process the image feature. A single dense layer will act as a fully connected layer which will convert those feature matrices into weights. Now we have feature encoder. It's time to build the decoder. Define embedding layer. a RNN layer to predict the next word, and remember to make return state equals true to get the hidden state from cells. 2 fully connected layer, and last an attention layer. In the call function, X is the current output of decoder, feature is the output from encoder, and hidden is the current state of decoder. Now first, feature and hidden state will pass through attention layer to get the context vector, then pass current decoder output through embedding layer and concatenate it to context vector as we saw in the architecture animation. Now we can push this output to RNN to predict the next word as output. Then pass output to fully connected layers and return the predicted word, current hidden state of decoder, and attention weights. Define one more function named reset state which will reset the decoder. Now we have everything ready. Let's make an instance of encoder and decoder. Define optimizer, loss function, and define a function to compute loss. Create a mask which will map 0 to false and rest values to true. Then compute loss using object. Assign the same data type to mask as loss has. Then multiply loss with mask and return mean. Hence we have loss function ready. Now make checkpoints instance to save model on a particular interval. This will restore last state of model from checkpoint so that if you break training in between, you don't have to start over. You can make a list to store losses so that you can plot it on a graph. Now make training function. Define a loss and set hidden state of decoder to 0 at starting of any image. Then define start token for decoder input. Now use encoder to get features from pre-processed image feature. Then push this feature into decoder to get prediction. Then use loss function to compute loss between real and predicted output. Notice this loss will be computed for word to word. That's why we use for loop here. Then we use current target as decoder's input to predict next word. Now calculate total loss by dividing loss with length of target or taking mean. Once you have loss, you can compute gradient and apply back propagation using optimizer. Then return the loss and total loss. So getting to final step to start training, define epochs and for every epoch get the starting time and define total loss variable. Now for every batch, feed that batch into train step function and on every 100 batch compute average batch loss. Store total loss in loss plot list to plot it later if you want, and on every 5th epoch save model checkpoint. Then finally print loss for particular epoch and time taken to complete one epoch. It will start training and will take time. So once training is finished, write a function to use model and predict on validation set. First, create a matrix filled with zeros to visualize attention. Get the current hidden state of decoder which is 0. Load the image using its path getting from function parameter. Then push it into feature extractor model to get the convolutional features. Reshape it, then push it into encoder to get the actual feature that decoder will use to generate sequence. Now define the starting token for decoder and make a list to store results. Repeat following steps till whatever maximum length of sequence we had in training dataset. Feed the features, hidden state and starting token into decoder to get prediction, current hidden state and attention weights. Store the attention weight into attention plot, get the prediction having maximum probability and use it to get the word from word index. And once decoder generates end token, just stop it there. Else, the current generated word will be decoder's next input and slice the attention plot equal to length of result. After that, we'll have a result and attention weight. Let's define a function to visualize attention weights. This function will take image, prediction and array contains attention weights. Load the image first and make a figure. Now repeat the following steps for every word. Resize attention weights to 8 by 8 matrix and define grid size. Add placeholder to plot image, set title as the current word and plot the attention weight matrix. Now choose a random image from image validation set, then get its real caption. Then feed the image to evaluate function and get the result and list containing attention weights. Print real and prediction result and use plot attention function to visualize model's attention, and at the end just plot the image. And here you can see for a particular word the model paid attention to which part, and above you can see real and predicted captions. Now here are 3 things you can remember from this video. Image captioning using image processing and natural language processing as encoder-decoder architecture to generate human-like caption for an image. Attention layer helps model to focus on relevant part of input using attention weights to decide more accurate target output. You can even plot attention on input so that you can see on which part the model paid attention with respect to output. That's all for image captioning. The link for source code and Bahdanau Attention explanation is in the description. Stay tuned for more updates through link in the description. And as always, thanks for watching.